Okay, minasan, konnichiwa, Zamurai Engineer desu. Again, we are here on our office, Taguig City University. So let us start and resume our discussion on reinforced concrete. Okay, so I will wait for somebody to confirm our sound. Okay, thank you for confirming the clarity of the sound. So therefore, we are going to proceed with our topic. Our topic in this particular segment is about doubly reinforced beam. So doubly reinforced. So by doubly reinforced, let us resume our discussion with this example. So already last meeting, we already told you that doubly reinforced beam are those type of beams that has reinforcement both at their tension side and compression side. So in both of the regions, compression and tension, there are metal or steel reinforcement. So take a look at our example. So I will need to turn off my video initially so that we can read our problem. So sample number 7, compute the bending stresses in the beam shown in the figure. N is equal to 10 and M is equal to 118 feet kilo-pounds. So what do you mean by N? N is the modular ratio. Okay, so M is the moment. So let us take a look first on the figure. So the figure looks like this. So in the figure, it is drawn. A is the actual section for the cross section. So meaning we have 14 inches at our beam width. So width of the beam is 14 inches. The height of the beam, or from top to bottom, from extreme top to extreme bottom, distance is 20 inches. Okay, and we have the concrete cover, that is called concrete cover, 2.5 inches. So that is concrete cover. This is the concrete cover. So from this point up to the center of the reinforcement, center of reinforcement up to the extreme fiber, 2.5, that is concrete cover. The same is true with the reinforcement at the bottom. So these are what we call top steel bars or top reinforcement. These are bottom reinforcement. So top and bottom reinforcement both have 2.5 concrete cover, meaning concrete covers the steel. Concrete is used to cover the rebars in order for the steel bars to be safe from corrosion. Okay, that is what we mean by concrete cover. Okay, that is one thing. Another thing is that it is the minimum concrete cover so that we have the most or the optimum bonding between the two materials. Okay, that is another explanation why we need concrete cover. So at least there are about three reasons for that. And you'll notice on letter B of the figure, take a look at the right hand side of your screen. You have the transform section, or we are using what? Transform area method. Okay, so in the transform area method, you'll notice we are using the crack elastic states. Okay, we already acknowledge that the concrete already cracked, and the crack is up to what? Up to the neutral axis. So you'll notice on the letter B transform section, the concrete participation is only on the compression side. Okay, compression side meaning we have what? 14 inches width, and we don't know the height. So we call it X. So the area of participation of concrete is X by 14. So 14X is the area for cross-section of concrete. What about the reinforcement? Take a look at the bottom reinforcement. So we have the area of steel bars, AS. So what is the size of steel bar? Number 9. And there are 4. There are 4 number 9 steel bars at the bottom. Okay? So number 9, that is equal to an area of 1 square inch. Okay? And since there are 4, so 4 times 1 is 4 square inch. So that is the area. Okay, so therefore total area is 4 square inch, that is AS, meaning area of steel. Okay, and we have to convert that area of steel to be converted to an equivalent concrete area. Therefore, what are we going to do? We know what we are going to do because last meeting we are multiplying that steel area by modular ratio. So NS. So N times AS. So NAS. That is for the tension side or the bottom bars. What about for the top bars? Take a look. The same size, number 9, but the top bars, we have only 2 bars at the top. So 2 times number 9. So therefore, the area of the top bars is 2 square inch. 2 square inch for 2. So 1 times 2 is 2 square inch. And the area of top bars or the area of compression side is what we call AS prime. AS prime, area of steel at compression side, A prime. The same is true with stress, FC prime. When we say FC prime, that is the concrete compressive stress. Prime meaning compression side. We are on the compression side. That is what we mean by prime. Okay? If we are talking about area, that is area prime. We are talking of stress of concrete, FC prime. Okay? So that is for the compression side. Okay? And for AS prime, therefore, the total is, again, 2 square inch. Okay. So therefore, if the area at the top bars is 2 square inch, multiply by the what? The factor that would make it to be converted to an equivalent concrete area. So because that is an steel area, we want an equivalent concrete area for that same function. Okay? So when we are talking of top bars, that is equivalent to 2n minus 1. Okay? We need to multiply A prime by 2n minus 1, as you can see on the figure. Okay? We have to multiply by 2n minus 1. Okay? Do you follow? Are we good? Do you follow? We are multiplying by quantity 2n minus 1. So multiplying by n, that is for the tension side or the bottom bars. So from the top bars, that is compression side multiplied by 2n minus 1. So there is a mathematical manipulation that would derive that expression y it is equal to 2n minus y. So at the moment, we are just looking at the figure. Let us accept it as it is. Okay, so returning back to the front of the problem, again, using that figure, we are being asked to compute the bending stresses, wherein we have n is equal to 10 and m is equal to 118 feet kilopounds. Solution. First, we need to locate neutral axis because the extreme fiber, the extreme compressive fiber at the top, going to the neutral axis, we need to find out what is that distance. What is the distance? So if we are able to find the neutral axis, we can find out what is the distance between the extreme compressive fiber up to the neutral axis. Okay? And therefore, we can use what? We can use the mechanics, okay, or we can use the theory of structure in order to put up an equation, formulate an equation that will say the centroid of area, okay, the moment of areas of the compressive side is equal to the moment of areas in the tension side. That is the equation we need to follow. So let us start with the compression side. Compression side, we have the area, okay, which is equal to 14x. That is the area of the concrete. Okay, so let us follow here. Area of the concrete here is 14 times x because x is from this point to this point. That is x. So 14x is the area of this. Okay, what is the moment of this area? So this must be multiplied by x over 2 because we need the moment with respect to the neutral axis. The neutral axis is this one, this point. This point is the neutral axis. This is x. So the moment arm must be x over 2. Okay? So 14x times x over 2, 14x times x over 2 is our moment of area from the concrete cross section, compressive side. Okay? Plus n times 2 minus 1 or 2n minus 1. What is this? This is the distance. 2n minus 1 is the distance from the the neutral axis, okay, that is the distance from the neutral axis up to the center of the reinforcement. Okay, so up to the center of reinforcement. Okay, because here you will notice this is 2.5 inch, 2.5 inch. So that distance, that is actually the distance from this point to this point, this the center of the top bar reinforcement to the neutral axis, that is x minus 2.5. Okay, that is x minus 2.5. Okay, okay. So that is the distance. So if you are looking at the moment of this area, we need this area to be this one. So area prime times 2n minus 1. So what is 2n? N is 10. So 2 times 10 is 20. 20 minus 1 is 19. So 19 times a prime. That is the area. Multiply by x minus 2.5. Because x minus 2.5, that is the distance from this point to this point. And that is the moment arm. Okay, so let's take a look. That is x here. X minus 2.5. That is the moment arm. So this whole thing is the area of the top bar reinforcement. Okay, which is equal to 2 multiplied by 2n minus 1. Okay, so that is for the compression side. What about for the tension side? Equal tension side. So tension side, we have the area of the bottom bars. What is the area of bottom bars? N times area AS. So 10 times 4, that is 40. What is the moment arm? The moment arm is from the center of the bottom bars up to the neutral axis. How much is that? That is what? Here, 17.5 inch. Okay? 17.5. So from this top to this point, this is 17.5. Because this is 20 minus 2.5, that is 17.5. So 17.5 minus x, that is from neutral axis to the center of the reinforcement. So we will use this as the moment arm, 17.5 minus x. That's why we have that equation. We have this equation. And since they are equal, so we can manipulate the algebra. Just a simple algebraic simplification, we can find out that the equation will result to quadratic equation. So using the completing the squares, using any method you want, we can solve for x. And x would be equal to 6.45. You can use your calculator, shift solve. You can input this into your calculator and press shift solve. Okay, and that is allowed in the board exam. That is allowed. Okay. So what will be the result? X is equal to 6.45 inches. Okay. Okay. We can now find out the moment of inertia. Okay. So the moment of inertia is again with respect to neutral axis. Okay, that is with respect to neutral axis. So therefore, we can solve for moment of inertia. This is the formula for the moment of inertia with respect to the neutral axis. Okay. If you don't know what I am talking about, you have to review mechanics. You have to review strength of material. You have to review structural theory. They have the formula for moment of inertia. Okay? So I can do this, but I will not do so. I will let you be responsible for the solution in solving moment of inertia. Okay, sir, malabo po. Dr. Z, sorry po, malabo. Sir, malabo po. Mag-HD kayo. Change quality. Good afternoon. So you may be experiencing low bandwidth in your connection. Automatically, your connection will be shifted to low quality video. That's why it would be hard for you to read, and it would be blurred. However, my connection is currently okay. There's no problem on my side. The problem is on your side of the Wi-Fi. I have a good Wi-Fi connection. It's colored green. It's green, so it is okay on my side. I cannot solve your connection of Wi-Fi, so thank you for the information, but I cannot solve it. Okay. So let's continue. After solving again the moment of inertia, so that is the moment of inertia. Okay. So we are now prepared to solve for the bending stresses. So let us solve for the bending stresses. Okay. So meaning let us solve for FC. Okay. FC is what? My over I. That is the formula, my over I. So 12. What is 12? This is just conversion factor of 12 inches per 1 foot. So converting foot to inches. Okay? Because these are inches. This is foot. So convert the foot to inches so that everyone would be in inches. Okay? So pound per square inch, that is PSI. Okay? So we are using M, which is equal to 118. So we are using Y, which is the distance, okay, from the extreme compressive fiber. that is equal to X actually, from this neutral axis to the top extreme fiber. That is 6.45. Okay, so if you solve that, you will get 1,357 PSI for your FC. So that is the stress on the extreme compressive fiber. Okay. What about the stress on the steel? So this is the stress of the concrete also, because that is the maximum compressive stress. So that is the FC. So Fs is the stress on the tension side of the steel bars. Okay. Fs prime is on the compressive side steel bars. Okay. So when we are using Fs, we need to what? To divide Fs by the N. So Fs over N, Fs over 10. So transfer 10 to the other side, or you can what? Multiply both sides by 10. So that's why we have 10 here. Okay. Again, 12 is just a conversion factor between inches and feet. So the same value of M, and 11.05 is what? Is the distance from the neutral axis to the center of the bottom reinforcement. Okay? And divide again by I. So IG. So therefore, if you calculate this one, the answer would be 23,253 PSI. Okay. What about Fs prime? So compressive strength. Okay. This is the stress of steel at top bars. Okay. Bending stress of steel at top bars. Okay. This is the bending stress at the bottom bars. So at the compressive side, this is at the tension side. So the same formula, my over I, we have to multiply by 2n. So 2 times, this is already a formula. It's a formula that we need to follow. So 2n is 10, so 12 is a conversion factor, m is 118, again 3.95 inch is y. This is the distance from the center of the reinforcement at the top bar reinforcement to the neutral axis. And then again use the inertia. So therefore, we always need the neutral axis, location, and inertia in order to find out all of these bending stresses. And if you compute this one, the bending stress of the top bars is equal to 16,624 PSI. Any question? Any clarification? You need further explanation? Which part do you need further explanation? Okay, nothing? So it is clear, so let us continue. Okay, before we continue this, let us be reminded that example number 7 that we just presented, explained, is actually what? Doubly reinforced beam. That is the doubly reinforced beam. Current practice, we are using the doubly reinforced beam. Almost 95% of the time, we are using doubly reinforced beam rather than singly reinforced beam. Okay? So singly reinforced beam, we just explained because there are still application for it. There are still application. You can still apply singly reinforced beam. Why not? However, because there are other reasons for it, that's why double reinforced beam is the way to go, and it is the current practice of engineers. Okay. So now, let us move on to the next major topic, ultimate or nominal flexural moments. Okay. So it is a brief introduction to the calculation of ultimate or nominal flexural strength. As you can recall, what do we mean by ultimate? Okay. As we can recall, what do we mean by nominal? We are always using the word ultimate and nominal in the same way, even if we are talking about timber design, we are talking about steel design, we are talking about reinforced concrete design, everything of this. Same way, we are talking about ultimate, nominal, we are talking about the same thing. Okay. So for this current explanation, okay, let us assume that tensile reinforcing bars are stressed to their yield point before the concrete on the compressive side. Take a look, listen to that very important statement. Okay? Tensile reinforcing bars are stressed to their yield point before the concrete on the compressive side of the beam is crushed. Okay? So I will show you the same figure here. So this is the tension side. So this is the compression side. So these bottom steel bars are what we call tension steel bars. Okay. So these steel bars should yield first before the compressive concrete, okay, section, the compressive concrete section will be crushed, okay, will be totally damaged. Okay? So this should yield first before this will get crushed. So we are talking about concrete here, we are talking about steel bars here, because we are looking at what? Crack model. The concrete participation on this tension side is negligible because these are already cracked. The crack is already up to the neutral axis, from the extreme tension fiber to the neutral axis. The compression side is already cracked on its concrete side. Okay? So the remaining material is the tensile strength of the bottom bars. So these bottom bars must yield first, meaning to say it must hit its yield point first before the concrete section here would get crushed by the load. Okay? So is that clear enough? Can you follow? That is a very important statement. Okay? So, Chapter 3, the whole Chapter 3 of the ACI code requires all beam designs to fall into this category. Okay? All, when we are talking of Chapter 3, all beam design must be that way. Meaning, the tension reinforcing bar must be stretched to yield point before the concrete on the compressive side is crushed. Okay? So that is a very important principle. Okay? Now, after the concrete compression stresses exceed about 0.5 FC prime, okay? So please be reminded or even memorize this one, very important. After concrete compression stresses exceed, if the compression side exceed 0.5 FC prime, they no longer vary directly as the distance from the neutral axis or as a straight line. Rather, they vary much as shown in figure 211b. Okay? Let us take a look at figure 211b. So 211b. This is the figure 211b. Actual compression stress variation. You can take a look. This is not a straight line. Supposed to be, this is triangle. The ideal is equal to beta 1 C. That is the equation. A is equal to beta 1 C. Okay? A is not equal to C. A is smaller than C. As you can notice here. Okay? But A is equal to beta 1 C. Okay? This is the shape. This is not a triangle. This is not a straight line. This is a curvature, no? Curve. There is a curve. Okay? That is what we mean by concrete compressive stress curve. Actual compression stress variation. But since this is very hard to model, it's very hard to model, it is very hard to formulate into mathematical equation, we will estimate the shape into this shape. So what we are doing is we are actually creating a simple shape model to represent this complicated shape model, actual variation, actual characteristic. This actual characteristic will be replaced by this simplistic model in order for us to be able to easily analyze mathematically the relationship, the equation, the stresses, and so on. That's what we are doing right now. Okay? So, they no longer, so after FC prime or 1/2 of the FC prime is reached, okay, there is no straight line. Okay, it is assumed for the purpose of this discussion that the curve compression diagram is replaced with a rectangular one, just like what I've said, with a constant stress of 0.85 FC prime. So instead of the actual stress, we are going to use a constant value. This is constant because FC prime is constant times another constant 0.85, so the resulting product would be constant. So this is a constant value, 0.85 FC prime, as shown in part C of the figure. I already explained that part. So the rectangular diagram of depth A is assumed to have the same center of gravity, and total magnitude as the curve diagram. That is the only condition. The center of gravity of the model must be the same with the center of gravity of the actual. Okay? Okay? This assumption will enable us to easily calculate the theoretical or nominal flexural strength of reinforced concrete, or the procedure. This is a simple procedure to obtain the theoretical moment strength. Okay. So number one, you need to follow compute total